Okay, so let's start the panel discussion. Yeah, thank you very much for attending. And today's panelist is Benoit Vicedo-san and Yamazaki Masahito-san and Yoshida Kentaroh-san. Yoshida Kentaroh-san over there. And the interviewer is Masashi Hamanaka, me. And the plan of this panel discussion would be as follows. So mainly three parts. The first one is to discuss the perspective of unification of integral systems. And the second one is relation to interaction between mathematics and physics. And finally, we discuss the various topics on this integral systems and so on. And I plan, this is very, very frank discussion and questions, comments, and so on. And so, yeah, please be relaxed. And okay, so firstly, I'd like to discuss the perspectives of unification of integral systems. Okay, so in this workshop, we discussed various topics on the unification of integral systems, such as integral deformation of 4D Chan-Simons and the Gaudian model, and so on. So, so I would like to ask the panelists the perspective of this research area. So positive or negative. So the future is bright or dark and so on. So I'd like to ask firstly, Benoit-san, please.
My perspectives on it's a very broad question. So on all these topics here, yes, I mean, I think for me, a very interesting direction is higher dimensions, where lots of things are unexplored. We know a lot of things about two-dimensional integrable field theories, even more about finite dimensional integrable systems, but I think high dimensions in field theory is very much unexplored. And there, as I'll explain in the lecture tomorrow, there are different perspectives which might be related. So we heard about non-commutative anti-self-dual Yang-Mills, which comes from non-commutative 5D Chan-Simons. There's also 5D 2 Chan-Simons and other in higher dimensions and other analogs. So there are different ways to go into higher dimensions, and I think it's very interesting to explore the relationships and the connections. And then there's related questions about what happens to the Godin story in high dimensions as well. Everything is related to Godin through 4D Chan-Simons and corresponding high dimensional versions of this theory. So yeah, I think, and you've written multiforms. I think this is also an interesting avenue. Yeah.
So far, there are many works about this integral systems, but your perspective would be this would be still continuing in the near future.
Yeah, I think there's lots of things still to explore. Yes.
Good. Thank you very much. Yamazaki-san?
Yeah, so let's see. First of all, for me, to some extent, the literature of integral models itself is vast and very diverse. But to some extent, it's always a mystery for me. Like that's my personal experience. There is always a lot of very clever techniques, or sometimes people write down the ansatz and solve it, and it looks very miraculous to me, at least to me. And I always talk with a lot of integral model people, and they tell me that what I'm doing is very black magic to them. But so it might be the both directions. But at least for me, many of the things are very mysterious. And then to some extent, that's because in a lot of the discussions of integrable models, it's a collection of knowledge, and people after a lot of trial and error. And it's great that the progress made that way. But of course, you have to be a genius to make progress that way. And that's not my way. I'm a more down to earth. So I try to make it understand it in a more down to earth way. And then that's always my question about integral models. But at least I know I feel that there are at least some framework to discuss the integral models in the somewhat systematic way, and then the Chern-Simons theory or the quantization thereof gives a way to approach this in a pedestrian way. Well, it's not necessarily the pedestrian for some people, but at least if you know some quantum field theories and things like that, and there is a systematic procedure to derive that, and that's the beauty of the approach as motivated by quantum field theory. And the hope for me is that those type of approaches will even unify different approaches to integrability. To some extent, my dream is to try to have a unified theory, grand unified theory of integrable models. And I even applied for a grant with that, and unfortunately that was approved. And so it's a grand unified theory of integral models, and it's natural to imagine that comes from the string theory. To some extent, that's string theory. So the lesson is that you go to even higher dimensions, it becomes rich clear, and then more structures there, and so that's the lesson. And then so my hope is that most of the ingredients you encounter in the literature, including many of the things on the slides, will ultimately come from some topological holomorphic version of the string theory, and to some extent that even raises the question of even maybe we should. My personal hope is not to just end there actually, but try to go beyond integrability. To some extent, if you start with string theory, there's a lot of geometric structure, mathematical structures, which is even beyond integrability. And then to me, integrability is the one particular structure which we encounter when we try to go beyond purely topological, purely holomorphic discussions. But we can do various different twists, or even the full sector of string theory, and that should give rise to novel mathematical structures. And so the hope is to try to, partly to understand the existing structures, but also try to find new structures, completely new structures, and start discussion there. So that's my kind of like a big picture for this type of activity.
Thank you very much. So your opinion is also very positive, I feel. Yeah. Okay, so what about Yoshida-san?
Okay, so let me state my opinions. And so actually, so I measure achievements on integral deformations of something. So for example, so I'm so for a long time, so I have engaged in studying integral deformations of 85+5 superstring theories. That is called Yamazaki deformations. And so the Benoit Vicedo here is a specialist on the pioneer of the subject. And so actually, so I followed Benoit's work, and so we studied the homogeneous Yamazaki deformations of 85+5 superstring. Actually, so at least in physics, so some people ask me, so why are you studying integral deformations? What is interesting to study integral deformations? So yeah, but actually, so now I have clear answers. So by considering the deformations, integral deformations, so we can find something unexpected. So for example, in the case of Yamazaki deformations of 85 superstring, so we got general supergravities beyond the usual supergravities. So we found very new notions. So actually, so by considering the integral deformations, it is very interesting to find out something unexpected. So actually, so okay, so tomorrow I will talk about Coulomb hybrid constructions in the context of four-dimensional Chern-Simons theories. But actually, so the developments or discovery of the Coulomb hybrid constructions for the principal color model was triggered by the study of four-dimensional nonlinear electrodynamics. So actually this relation is quite unexpected. So it is very interesting. So for the four-dimensional Maxwell theories has been related to two-dimensional integral models. So that's why, so by studying integral deformations, we may get experience to find something unexpected. So this is a very interesting and fascinating point. So actually, So whole integral deformations in the context of four-dimensional channel theories was triggered by four-dimensional deformations of integral four-dimensional Maxwell theory. But so I expected that the Coulomb-Hilbert constructions should be related to the four-dimensional anti-self-trial Yamil theories. So that is also related to the deformations of four-dimensional Maxwell theories somehow. So that's why. So I guess that so Coulomb-Hilbert constructions may open new arenas to study the nice connections between four-dimensional gauge theories and two-dimensional integral models. Okay, so anyway, so that's my opinions.
Thank you very much. Please keep mic. Okay, so I remember yesterday Yoshida-san said there are many things to be studied. So do you recommend young people to study this one?
Actually, I'm sure. So anyway, so Coulomb-Hilbert construction is a nice windows to study the integral deformations. Actually, so that is closely related to the TT bar deformations and root TT bar deformations. And interestingly, so such deformations can be removed by performing Fourier transformations depending on the field. So that is quite a mysterious point. So I want to understand the underlying physics related to these Fourier transformations. So yeah, probably I think that's so very interesting physics should be behind these Fourier transformations. And yeah, probably I think that this would be a nice subject to tackle for young students or young researchers.
Yeah, so if you are interested in, please join Yoshida-san's group. Okay, so is there any questions or comments from the hall, from young people? There is a specialist of 4D Chan Simon, Sakamoto-san. How about it? It's okay. Outside the collaborator of Yoshida-san. Yeah, Yamazaki-san also, yeah. Yeah. Yeah, very important part of it. 鉱物があるので。
本当に何も考えてない。
ポジティブはネガティブ
Yeah, basically, positive, or,
Did you enjoy the collaboration so far?
yeah, I enjoyed to study how to unify integrable system from perspective the higher dimensional gauge theory. So, and including the integrable lattice model. In particular, I think the most interesting point of the 4D Chan-Simon framework is that the framework can unify the integrable lattice model and in continuous integrable field theory in a single framework. So I think I wanted to understand the whole quantum aspect of the both lattice and the continuous field theory in a single gauge theory. So I think the 4D Chan-Simon theory has such a power to understand such unified mathematical structure of the both models. Yeah.
Okay, thank you very much, Sakamoto-san. I remember you are student of Yoshida-san. What's your name?
Yes.
Yeah.
He's one of my students. So actually, so he studied the 4D Chan-Simon theories for his graduate thesis. He's now master course first years. And so yeah, last year, so he wrote a thesis for 4D Chan-Simon.
My bachelor thesis, this reference Vicedo-san and Yamazaki-san. sorry for my lack of knowledge of integrable. I have a question. I learned integrable triangle, rational, elliptic. In this case, we consider rational integrable. Other integrable it's in this 40 chance as a other case integrable it can relation 日本語ですいません。
トリゴノメトリックとかエリプティックとかそういう意味ですか？はい。トリゴノメトリックとかエリプティックはそういう意味ですかね。はい。Yeah, so let's see. So for trigonometric and elliptic model, so that's the choice of the spectral curve. Okay, maybe I shouldn't call it the spectral curve. But anyway, the curve for the spectral parameter takes value. So let's call it the spectral curve. So, and it's a part of the curve, holomorphic curve in the 4D Chern-Simon theory. And then, for example, you can take that curve to be elliptic curve. And then that will realize the elliptic models. Partly because when you try to do the Chern-Simons perturbation theory, you have to solve that theory on there, and you get a propagator, which is a Green's function on the Riemann surface, which is a torus, and then you get a theta function, for example. And in fact, there are a lot of interesting discussions. So yeah, in fact, in many of my lectures, I try to do the rational case, but indeed there are a lot of subtleties in the trigonometric and rational in the elliptic case, for example. And then, for example, for the trigonometric case, there is a deformation parameter which people noticed. That's a 6 vertex model with the non-trivial field turned on. And then that corresponds to the fact that this trigonometric case corresponds to a cylinder. And on the cylinder, there are boundary conditions you can play around. And then that corresponds to deformation of the theory. But there is a counterpart, which is an 8 vertex model, and people didn't find any parameter. There are even recent proofs that you have a general field, it's not integrable. And then that corresponds to the fact that on the elliptic case, you just have a torus. And then there is no such parameter to play around. And even beyond that, for example, if you do the general gauge group on the elliptic curve, and then there is a moduli space of flat connections on the Riemann surface, and then that will generate the extra dependence of the R matrix. So in general, that's what you get is the solution of the Yang-Baxter equation with the modification called the dynamical Yang-Baxter equation, which is the related with the elliptic quantum groups. And you get a solution of the usual Yang-Baxter equation only when for rigid bundles on the elliptic curve, which is PGN, for example, PGL. So some of the structures people find by studying one by one, such as the trigonometric case, there is a deformation, but in elliptic case, there is no, and things like that, which people found has a natural incarnation in the context of the 4D Chern-Simons theory. Now, so that's about a lattice model, solution to the Yang-Baxter equation. But now, if you come back to the story of integrable field theory, not the integrable lattice model, which Benoit was describing, and then you can also, that story actually works even for higher genus Riemann surfaces. And then that you can discuss that in complete more generality. You can even try to discuss at least partly cutting of the Riemann surface into two and gluing together and things like that. Now, the chiral Potts model I was describing this morning is again on the lattice model side, but that was peculiar one with a very higher genus Riemann surface. And so that's a very peculiar one. So, and it's very rare to find such a model. So if anybody could find such a model with a higher genus spectral curve, and that's all, you might immediately become famous in the literature of integrable models. So that's a very challenging problem, but that could be a very rewarding project.
Thank you.
Thank you very much. So I look forward to your master thesis. So could you send it to me? Then I can give you the mugi choco. Okay, so is there any other questions or comments?
What's your perspective, Hamanaka-san? So
my
you're also one of the experts, no?
very positive, yeah, of course. Very positive.
Somebody should have a negative opinion, no? Yeah, I mean, often I get a question like, what's new in the end, for example. And yeah, of course, yeah, there are a lot of new results, like construction, new integrable field theory, etc. But yeah, well, of course, a lot of people are curious, like, in the end, what's the new result?
Yeah. Is there any comments? There's a Takasaki-san here. Takasaki-san, you studied self-driving mills and hierarchy, and recently you also studied the relationship of your theories and the Cauchy matrix approach and so on. So how about your opinion or perspective? Do you have?
Well, I don't have a definite perspective, but rather let me mention that when I started studying integral systems in the beginning of 80s, I started from the Sato theory. It's a theory, unified theory of solid equations, and Sato proposed to study higher dimensions systems. And at that moment, I thought one candidate will be the self-driving mills and the self-driving gravity. And then I started to study. And well, and then at that moment, finally I thought that the anti-self-driving mills equations and gravity equations cannot be the good candidate for the higher dimensional solid equations. So at that moment, I abandoned that project and I moved to some of the things. So it was quite surprising that now the self-driving mills equations are revived to be a candidate for a unified theory. But even I'm surprised. I have to confess that when I started to study self-driving mills, I have to study Twitter theory. And so I read some papers, and Penrose had quite optimistic perspective to of Twitter theory as a theory of physics. But at that moment, probably it was only Roger Penrose that who thought in that way, and many people simply thought that Twitter theory is just a theory of mathematics. So I was quite surprised when Twitter theory was applied to physics by Britons through Twitter string theory. And so I had to change my way of thinking. And now I again have to change my way of thinking. Because now Twitter theory should be unified to Chern-Simons theory, this is starting theory, and I never imagined such a possibility. So I'm simply surprised.
Okay, thank you very much for valuable comments. Do you have any comments on their answer?
I find it a bit difficult to imagine this one unified theory which we are looking for, because from my understanding, we want to get one theory and then we reduce its dimensions and get various integrable systems. But these systems might have different dimensions. And I got the impression from previous presentations that we need starting theories of different dimensions to get, for example, a one-dimensional or a two-dimensional integrable field theory. So I'm wondering if there is these problems with dimensions is actually a problem, or can we do something about it?
to comment on? Yeah.
I can start by saying that 3D BF theory is actually a reduction of 4D Chern-Simons theory. It's a level 0 Chern-Simons theory. So as Yamazaki said, 3D Chern-Simons you can get from 4D Chern-Simons by reduction. In fact, you get level 0 Chern-Simons, which is secretly BF theory, 3D BF theory. So the mother theory of 1D integrable systems is obtained by a reduction of the mother theory for 2D integrable systems, or 2D integrable field theories. And it's the same thing as Yamazaki explains. If you go up to 6 dimensions, which is the mother theory for 4D integrable field theories, its reductions are 5D and partially holomorphic and 4D Chern-Simons. So all of these Chern-Simons theory are sort of a hierarchy of theories which are reductions of one another. So the mother theory upstairs, which I know of best, is 6D Chern-Simons, holomorphic Chern-Simons. This reduces to all the other ones. So I think it's fair to say that there is a mother theory in high dimensions which has reductions to all these lower theories, which are mother theories for the individual integrable field theories in those dimensions. Right? Do you want to add something?
Yeah. So, well, maybe one comment I have is that so in general, of course, we shouldn't expect the sign chain of things, etc. So we are talking about the series in different dimensions. So here we are not necessarily talking about the duality in the most naive sense, for example. So we are talking about different series. For example, you compute, well, it's partly topological, etc. But we are not necessarily claiming that it's the series are completely equivalent and things like that. So, but I think we are rather talking about some aspect of the theory, like integrable structures and how it's deformed, how it's interpret. And so that's so some discussion is somewhat similar to, well, in fact, I'm raising that because there was already, I noticed that there are some people asking about the comparison with the AGT type conjectures. And there, it's again, not, you can call it AGT duality, but it's not a duality in the standard sense. So if you compute that, in that case, you have a 4D theory, 2D theory, and if, for example, if you compute the free energy for generic observable, the 4D theory, even the scaling is completely different from 2D. So that's a basic thermodynamics which you learn. So, but nevertheless, in those cases, there are some nice observables on one side captured by the other side. So as long as some information is concerned, you can make comparisons and then keep track of that in the various chain of series by going through the dimensional reductions. Yeah, so I'm not sure if anybody has articulated that in this particular context, but at least we are looking at some algebraic structures arising the integrable models, integrability in this particular context, and then we can keep track of a variety of series. And well, of course, I should also add that the area of integrability is rather diverse. There are always different aspects of integrability, and we are also trying to unify different aspects. That's the point. But honestly, it's hard to come up with a single framework that explains everything about the integral models. So I think it might be actually tall order, but at least but maybe we don't resolve everything in a single literally it's a single thing. But at least it's nice to have the framework where different aspects of integrability can be related. So indeed, for example, Sakamoto-san mentioned the connection between integrable lattice models and integrable quantum field series. And at least for me, one of the surprises when I started working on integrable models is that people working on integrable lattice models, representation of Yangians and integrable field series, like talking about the sigma models and symmetric coset. And sometimes it's a different community sometimes. And then, well, of course depends, but it feels like a different community because there are different type of techniques are used. And so, but of course, we are working on closely related stuff. And to rejuvenate the field and then make new progress, I think it's important to try to connect different perspectives. And for that, I think this approach is going to be tremendously useful. And there are indications that that's working already. If you want to make one.
Okay, so you're probably asking us, so you two have already mentioned a lot of things. So yeah, probably. So okay, so I want to add some comments from the perspective of particle physicists. So we already asked us, there are a lot of mathematicians here, but at least to me, so looking for unified theory is something like looking for unified theories of particles. So the probably as you know well, so the integral models have been discovered case-by-case analysis, and some integral models are found, and so another model is found, and so then So there are a lot of integral models have been found independently. So that is something like discovery of particles in collider physics, collider experiments. So I think that's so at least for my particle physicist perspective, so it is quite natural to look for unifications of integral models. So this is kind of analysis, but okay, so this is my opinion.
Thank you very much. Are you satisfied? It's okay. You are a graduate student? Can you introduce yourself?
So I'm in the G30 physics undergraduate course here at Nagoya University. I'm a fourth-year student here, yes.
Thank you very much. Okay, okay. Yang-san, do you have any?
On what? On what?
Every
topic.
From mathematician.
Ah,
Are you mathematician?
yes. And yeah, I should comment that it is a very pity that almost here there is almost no student in mathematics. It's a very pity.
Okay. Okay. From hall, there is any other comments or questions? Okay, how about from online participants? Please unmute and make a questions or comments. No comments?
Can I make a
Yeah, please.
comment,
Please.
Hamanaka? So I'm Frank Nijhoff. I've only seen part of the. Can you hear me?
Yeah, yes.
Okay, so one comment I would have, and it's also mentioned already, is that to me the discreteness is an essential aspect of integrability, and I don't mean only lattice models that appear in statistical mechanics, but in fact quantum field theory on the space-time lattice in any kind of dimension. And that is kind of a subject that has only started, and discrete integrability has been popular or became popular a little bit in the start of the 1990s. But I think this discreteness is an essential aspect of all integrability and should also appear in the quantum field theory setting. And so far, one drawback is that I don't know yet of a fully discrete version of either self-dual Yang-Mills or the various Chern-Simons theories. But they do exist. And for instance, in a system that I've been involved with, the so-called what I call the Darboux KP system, there is a discrete version which is closely related to the Chern-Simons theory. And so that is an aspect that I think should play a role. One big drawback in bringing discreteness is that you lose in some sense connection with geometry. There is a thing called discrete differential geometry, but it is not in the same level or same standing as ordinary smooth differential geometry, in the sense that you lack basic transformation rules. And one of the aspects that is essential is the aspect of composition of functions, compositions of discrete functions, for which there is not yet a full understanding how that would work. And that would be needed to have a kind of transformational theory that lives on that allows you to develop a true discrete geometry that you would need to make the whole theory also geometrically sound. So that is kind of my comment, that somehow we would need to look for discrete versions of Chern-Simons theories and understand their geometric meaning in the discrete space-time sense.
Yeah, thank you very much for valuable comments. Yeah, I understand the importance of the discretization of integral systems. That it's a very popular topic in integral systems in mathematics. But in physics, discrete. So in your sense, discretization have no physical meaning as far as I know. So in fact, I've never studied the discretization of self-Yang mills and so on. But yeah, in the near future, if there is a physical meaning, for example, quantization of space-time, naturally give rise to the discretization of, yeah, in your sense, then
Well, that is indeed that is precisely where I think it should kind of go in the direction also with quantization, which is also a form of discretization, as we know. We should think along those lines, or discrete space-time underlying kind of foundational physics.
Yeah, I think I would say, thank you for the question. I think that's a very profound question. And I just say, well, of course, I'm too young to know that, but indeed, it's one of the motivations for the day of school is to started discussing discrete review and everything was the program of discretizing the quantum field theory and make everything regularized. So it was at least one of the initial motivations was to introduce the UB regulator to make everything finite and compute things in a controlled way. Well, so that's, of course, that makes things less universal because you're choosing a particular UB regulator. But in the case of integral models, there is a systematic procedure. But in general, that involves going to the UB. So you're not committed, you're going beyond the conventional quantum field theory, but choose a particular UB descriptions. Now, of course, for the specific case of anti-safety Yang-Mills, I don't know. But in general, what this type of discussion suggests is that there is a big elephant in the room, which is the actual string theory. So, namely, we are talking about the holomorphic Chern-Simons, and that's a gauge theory, for example. But it ultimately comes from a string theory. And what string theory is different from a quantum field theory, of course, it's a theory of quantum gravity, but there is a specific length, for example, string scale, and the Planck length, for example, which is related to string coupling constant. And that's the scale where the conventional description in terms of the effective field theory breaks down. So something new we expect to happen. And indeed, the classical concept of geometry, we will replace by some quantum geometry, which is like a discretization, some version of the discretization of space-time. And working that out is an extremely challenging problem. It's a $1 million problem, in my opinion. But people try to look at it in some different contexts. For example, let's take a topological string theory on a toric Calabi-Yau, for example. And in that case, there is a discussion of the crystal melting, and that's the case where we expect the discretized version of space-time, and which is very, very discrete. And only in the thermodynamic limit, this discretized configuration reduced to the classical space-time. And so there is a discretization happening, and which is closely related in that context to the concept of geometric quantization. So in the phase space, there is H bar and then quantize. But somewhat similar in spirit, if you have a geometry, you can do the geometric quantization on the space-time. So that there is a kind of like H bar, which in that case is a string coupling constant, and that discretizes the space-time, and that's that type of discretization should be related with this type of structure. Now, I don't know. So in that particular case, there is an underlying algebra, which is this algebra of affine Yangian, or more generally, I generalize it to Kuiper Yangian. So which is again some integrable model type structure. So which is some version of this coming from some 5D Chern-Simons and things like that. And so even in that case, at least in that particular example, we have a signature. Well, it's a very simplified model of geometry, but nevertheless, we have some discretization of space-time, and then the emergence of classical space-time, classical geometry in some limit, and one of the guiding principle there is the infinite dimensional algebra, integrable structure kind of, and so I think so in that example, it was instructive to think about integrability. So that's a very specific example, but I do hope that integrability might be one of the ways to control the geometry arising from intrinsically string theory.
Okay, thank you very much. So are you satisfied? It's okay.
Yes.
Okay. So is there any questions or comments from online? No questions? Okay, let's go on the next topics. So then, please. I'm sorry. これを、カーソルを。Okay, so next topics is more generic. So I'd like to discuss the recent interaction between the mathematics and the physics. So far, there are very fruitful interaction between physics and mathematics, but it's now booming like never before, I think. For example, pure maths have been applied to solve long-standing problems in physics. For example, operator algebra applied to SPT phases or black holes, and algebraic topology applied to anomaly, and so on. And there also a progress on mathematical formulation of quantum field theory, such as Kossel-Gideon factorization algebra and homotopy algebra, and so on. So I'd like to ask the frank opinion from the panelists first. Benoit-san, please.
So I think, so I can comment on Kossela-Guilliam factorization algebras. So I think factorization algebras in general are very hard to describe and quantize, but a very simple setting is the setting of topological quantum field theories, which is described by locally constant factorization algebras. And then the next best thing is holomorphic factorization algebras. So this is why I think there's a lot of interest in the mathematical community in these topological holomorphic field theories, because they have descriptions from a mathematical point of view in terms of locally constant or holomorphic factorization algebras. So it provides a very interesting mathematical framework for studying this kind of field theories that we're interested in from an integrable perspective. So all these topological holomorphic gauge theories have frameworks in the mathematical literature for approaching their quantizations and that's those things. So which are related to BV formalism and so on. So and homotopical algebra. So I think it's that's probably why there's a lot of fruitful interaction these days between mathematicians and physicists in this particular area.
Yeah, I agree. Yeah. So how about Yamazaki-san?
Yeah, so one comment I have is that well, I'm not too old, but I'm old enough to know that what was happening in like 20 years ago. So, and then, so I mean, of course, there's a lot of interactions already. For example, in the 90s when cyber witness theory came, for example, and then people started discussing that, and then the interaction between math and physics has been continuing. And but one at least in my opinion, a little bit of difference from what was happening in those days is that quite often. I mean, for example, you invoked a lot of the mathematicians then invoke physics as a kind of like a black box. I mean, I attended so many talks saying that, okay, I don't understand physics, but there is some black box and then there is a conjecture. So there is a miraculous identity. I don't know what it is, but let's understand the meaning of that. And then let's prove it in a completely different way in mathematically. So that's completely fine way of doing mathematical physics interaction. Like, so physicists behave like an oracle, but sometimes incorrect, sometimes correct, but, and then mathematicians get inspirations and start developing things, and so much so that the physicists don't understand at some point. And that's of course one good mathematics physics interaction, and there is nothing wrong with that. But to some extent, after I've seen this many years, I have a lingering feeling that we should try to come to the actual stuff, which is inside the black box. We should try to open the black box and then try to discuss the actual thing. And of course, the black box is the quantum field theory, and it's actually very hard to know. But of course, we don't understand the non-perturbative formulation of QFT, mathematical, etc. But actually, even physically, quite often we don't necessarily understand the full formulation of quantum field theory, physically even. So so at least what the physicists kind of tend to know about the quantum field theory, at least we should try to understand, to make it in the actual playground for the mathematical physics interaction, not as a black box. And from that perspective, of course, the topological quantum field theory is one thing, but that it's great to see that there are a lot of activities in formulating the theory. For example, in the vertex operator algebra form net and axiomatic formulation, but also this somewhat new approach by these factorization algebras. And it's also great to see that the factorization algebras are motivate people in a somewhat abstract language. The type of series a lot of physicists are interested in, like a supersymmetric field series, N-4, Yamels, and then their relations or defect inside it, or non-invertible symmetries acting on them. All these things can be discussed. And then even the renormalization flow, all these things can now be part of the mathematics where people can discuss that. And I think that's the aspect which I find amazing in the recent developments over the past few years, compared with what was happening 20 years ago.
Thank you very much. I would like to announce that the next issue of Japanese magazine, Suri Kagak, is organized by Yamazaki-san, and that title would be Mathematical Aspects of Topological Quantum Field Theory, right? Yeah. I see.
Yamazaki-san wrote an article about it.
Very good, very good. So let's enjoy, yeah. Okay, so Yoshida-san, please.
Okay, so I want to make comments for the relations between mathematics and physics. So in the previous talk, I talked about the Coulomb-Hilbert constructions of integral deformations in three-dimensional principal parallel model. So that is closely related to the four-dimensional nonlinear electrodynamics. And actually, so the flatness conditions in three-dimensional principal parallel model corresponds to self-duality conditions. So that condition ensures the self-dualities of the theories. So the physics should be directly related to the flatness of the dimensional principal parallel model. That is quite surprising, at least to me. And so then, the Lagrangian was given by an arbitrary function f. And so then, the energy momentum tensors in two-dimensional principal parallel model, deformed principal parallel model is also written in terms of f. And so the energy momentum tensor depends on arbitrary f. So then, we need to impose some physical conditions for energy momentum tensors, positive energy conditions or NX conditions or something like that. So we can impose some physical conditions. So for example, the physical conditions for the energy momentum tensors in the context of energy four-dimensional nonlinear electrodynamics corresponds to the weak gravity conjecture bound. So that was shown by Nomikum et al. And so directly related to real physics. And so such conditions may be related to some conditions for two-dimensional principal parallel models. For example, the classical integrabilities can survive quantum collections, and the quantum integrability can be shown or something. And so probably I think that real physics may be related to integrabilities in two-dimensional integral systems. So it's quite surprising. And so yeah, anyway, so I would like to talk about some relations to models. And so anyway, so this is my comment.
Thank you very much. Okay, so is there any question or comment from the hall? Yeah, please. Student.
Thank you. I'm a master student supervised by Professor Hamanaka, but it's deeply regretting that I, with my supervisor, have completely different research interest. Professor Hamanaka is familiar with gauge theory physics, but my research interest is gauge theory from mathematics. We know that from science revolutionized, discovered by Professor Donaldson last century. The central idea of gauge theory is the counting problem. Following Professor Donaldson and Professor Top's work, there are two lines in gauge theory over the past decade. The first line is about Top's work. For example, the Kaplan-Witten equations, counting problem, the Jones polynomial equations counting coefficients over the Jones polynomial is equal to the solution of the Kaplan-Witten equations. And the next problem is Professor Donaldson's generalization of the Yang-Mills theory into the higher dimensions, such as G2 manifold and Calabi-Yau manifold, which the corresponding in a unification framework, we can write the Yang-Mills Higgs functional and get the corresponding monopause equations in higher dimension, which is my interest recent. But my question is, I'm sorry, Professor, I wanted to ask these two program, is this program interesting in physics? For example, Donaldson's work and Tom's work recent. I'm sorry, I'm a little nervous.
Well, let's see. Yeah, so I would say that, well, first of all, so it's a part different aspects of studying supersymmetric gauge theory, for example. So it's one aspect of supersymmetric gauge theories, but of course, this is a little bit of a general discussion. But of course, once you specify a particular gauge theory, like a 4D n equal 2 superior Mills, for example, topological twist, or 4D n equal 4 Kaplan-Witten twist, and then of course there is a separate question, like you write down the differential equations, like do the counting, and then you get the enumerative invariance, for example, and then what type of information you can extract. Now, it is true that some aspects of physics discussion, some aspects of mathematics discussion are somewhat perpendicular. For example, if you look at the recent developments in the the 4D gauge theory discussion, of course, one of the discussions is to detect the smooth structures, for example, differential structure on the geometry, four manifold geometry, and then typically if you talk with a physicist, they don't care about they don't care what type of for example, 4-dimension R4, there are infinite countably many or something. There are so many differential structures. But if you're a physicist, R4 is just R4, right? It is true that some interest is a little bit different. But nevertheless, there are some somewhat more concrete things. For example, instead of talking about the moduli itself, you can, for example, do the counting, specific counting problems, which is very close to the, for example, Donaldson invariance or Seiberg-Witten invariance. And in those contexts, it gives us a specific counting problem, enumerating invariance and the generating functions. Now, of course, computing these one by one is also interesting problems, interesting combinatorial structure appears. But one of the things people find in these days is that counting is one thing, but once you have a counting and it finds a nice expression like a modular form, so there should be an explanation why the generating function takes a nice form. And the typical explanation is that there is an underlying algebra. So there is an underlying algebra, and then there is a general way of defining it, which goes by the name of cohomological Hall algebra. For example, starting with the quivers, and then there is an algebra acting on that. And if you make so that's like a positive part, and if you take a double of that and combine them together, you can find structures like a Yang, for example. And then, or like in a simpler case, it's a so-called Nakajima story, affine Katsumudi algebra acting in the instant moduli space, and then you get a character of the affine Katsumudi algebra coming from the counting of the gauge theory, for example, instanton counting. So in the end, even if you're interested in the counting problem itself and by studying the moduli space of solutions, as long as you talk about specific counting, you get the generating functions, and you expect there is an underlying algebra. And that's a very general concept of BPS state algebras. And typically, it's a very intricate algebra with many, many generators, interesting relations, and then typically has some flavor of some version of integrability, because it's an infinite dimensional algebras and some not necessarily integrability in the narrow sense, like affine Katsumudi algebra and things like that, but a nice algebraic structure emerging from there. And in some cases, you can even talk about the R matrices or things like that, which is even closer to integrability. But that's an example of algebraic structure. So I would say that things are different. It's a different aspect, but not necessarily fundamentally different. So for example, I was mentioning this affine Yangian before, but it turns out that affine Yangians do appear in some counting problems in the Donaldson-Thomas invariance, for example. So I would say that it's like we are talking about the different aspects of the well, different aspects, but fundamentally closely related the ingredients is actually hiding behind that. That's I would phrase it.
Professor.
Is there any other questions or comments? So Moriwaki-san gave a mathematical formulation of quantum field theory, the review of these topics this year. Do you have any comment?
Comment on this.
Yeah.
As mathematician, I feel like the strength of the mathematics is give a language for the physics. So I'm very interested. In fact, like factorization algebra provides a very nice language for gauge fixing, and But so so it give us a language for QFT somehow, but part of it is but language for QFT. So how do you think about the language for the string theory and M theory? Of course, it's a very difficult question, I guess, but do you have any perspective? What kind of mathematics is needed? And
that's a very difficult question, but I would say that actually one of the motivation for the Battarin-Vilkovsky formalism came from string theory, actually string theory or string field theory. So for example, if you do usual non-abelian gauge theory, you can invoke the Battarin-Vilkovsky formalism, but it's in a somewhat trivial way. I shouldn't say too trivial, but relatively, trivial way. It helps to understand the structure, the ghost and everything, but it was not a requirement, I would say. Because whereas if you go to string field theory, Battarin-Vilkovsky is somewhat really becomes really necessary. And in fact, Costello himself, I never confirmed with him directly, but he started as an expert on the ground fit, some aspect of ground fitting theory, and then modular special Riemann surfaces, and that's how Battarin-Vilkovsky came in. So I would say that the underlying aspect of that is that, I think I would say that you can actually pursue the Battarin-Vilkovsky type or the factorization algebra type formalism, but not to the type of string theory the ordinary string theorists might think about, which is the first quantized one. But there is a second quantized version, string field theory, and the string field theory has a very good connection to the Battarin-Vilkovsky formalism. So and of course it also has a nice connection to modular special Riemann surfaces and everything. That might be one good way to phrase it. And then it's not unrelated to this Chern-Simons description, because in the original paper where Witten discussed Chern-Simons theory, precisely as a version of the, so it's actually long distance limit of the string series, cubic string series Witten code. And then if you replace the product by Moyer star, and then that's the Witten's cubic string field theory. And in the original paper of the Witten, he discussed the connection of Chern-Simons in the A model and a holomorphic Chern-Simons B model from starting from string field theory. So I think, and it's fair to say that the string field theory has been existing as a general framework, but not many people has been working on that, partly because it's complicated, and partly because it's not easy to extract concrete results. But there are a lot of developments, especially in the superstring field theory and superstring perturbation theory in general, in the formulations recently. And then in particular, for example, there is one of the achievements that there is a construction of heterotic string field theory for heterotic theory, for example. And I think all these things are fascinating, and then I'm sure that there is new mathematics. Pursuing that might be one way to try to understand string theory in a more mathematical, rigorous way.
Thank you very much. Okay. So Matsunaga-san studied so far homotopy, string field theory and homotopy algebra formulation. How about your opinion?
First, perturbative string field theory or superstring field theory completely fit into factorization algebra. So, I'm not an expert of integrability. So, I want to ask some naive question about integrability. So, I'm interested in whether or how
the integrability fit into factorization algebra? So do you have any opinion?
To make a comment?
So yeah. So do integrability is non-perturbative property or perturbative one? I'm
Property or what?
So people call this, some model has integrability, so, but I'm not sure whether integrability means perturbative property of quantum field theory or non-perturbative one. So
So yeah, here you're talking about quantum integrable field theories. I think it's a completely open question how factorization algebras are used to describe integrable field theories. I don't think it's been explored yet, but I think the way they should be used is through the concept of higher D. Chern-Simons theories, 4D Chern-Simons and so on. So these are the physical theories you want to describe, which hard code the integrable structures of certain quantum field theories, if you could quantize them. And these are holomorphic topological field theories which have a description as quantum field theories in terms of factorization algebras. So I don't think this has been explored much yet, but I think this is the avenue to pursue for understanding how factorization algebras are used in understanding quantum field theories, which are integrable via the description of 4D Chern-Simons theories and high dimensional versions. Yeah. Do you have a comment? Or?
Yeah, so for example, one brief comment is that okay, maybe not brief once I start talking, but for example, so if you have a holomorphic topological theory, and then you can try to first the dimension reduce to each of the directions, and then for example, if you reduce a topological direction, you get a topological factorization algebra, which is called the for example, if it's two dimensional, it's called the E2 algebra, for example. And then if you reduce to the holomorphic direction, you get a holomorphic theory. Which if you take a cohomology, it reduces the vertex operator algebra, for example, vertex algebra maybe, but depending on what you assume. And so in general, so the holomorphic topological theory will be a setup where this E2 algebra structure and the vertex operator algebra structures are kind of combined together. And then that's that's more or less how Costello tried to formulate in one of his papers. Having said that, it's actually more subtle than you might imagine. For example, because there is a holomorphic topological direction, I describe it in a kind of decoupled way, reduction to here, reduction to there, and combined together. But what we are learning, at least in the quantum theory, is that these two directions are not decoupled. It's not the direct product, but one is fiber non-trivial of the other. And that's there are a lot of indications of that, like a framing anomaly and all that. But if you like, you can also even start with that classically non-trivial fiber, etc. So yeah, or more generally, like a holomorphic structure might be transfer structure inside the four manifold. So there are a lot of so that suggests that there is a non-trivial when you try to combine these ingredients like E2 algebras and the BOAs type structures, or I shouldn't say instead of BOA, I should say holomorphic invariant factorization algebra. So when you try to combine them together, there is a non-trivial interplay between the two in the actual quantum theory. And I think I don't. So it's in this particular example, you can say that it's partly understood by roundabout way, but not necessarily intrinsically factorization algebra way. So if you try to combine together, there are some obstructions, or like one is fiber non-trivially, and it's not as simple as naively putting things together. And I wonder if there could be a more general lesson. So because you can try to keep the, I mean, there is a many higher dimensional series, supersymmetric series, and there are various different topological twists, partial topological, partial there, and so there is a lot of choices of the twist in a different supersymmetric field theory, and that will correspond to different ways of formulating the theory in different directions and everything. And can we formulate that? I think that could be one of the challenges in the factorization algebra.
Okay. Thank you very much. And due to time limitation, I would like to ask the online participants for the questions or comments. Do you have? A brief comment would be preferable. I'm sorry. No question? It's a good occasion. No? Okay, okay. If not, so let's thank all the panelists and all participants. Thank you very much.